projects. In this video, we are going to explain about the project entitled as Yield Diagnosis and Tuning for Emerging Semiconductors during Research Stage. So, before getting into the video, let me give you the brief description about the project. The title refers to the methods and strategies used to identify, analyze, and improve factors that affect manufacturing yield early in the development of new semiconductor technologies. At this stage, materials, devices, and processes are still experimental. So, engineers focus on detecting defect mechanisms, understanding variability, optimizing fabrication steps, and implementing feedback loops to enhance performance and reliability. Early yield tuning helps accelerate technology maturity, reduce development risk, and ensure a smoother transmission to pilot and high volume manufacturing. Coming to the abstract addresses the challenge of transmitting new semiconductor devices from laboratory research to mass production, a process that is both time consuming and research intensive with significant effort focused on improving yield. Traditional machine learning approaches for yield optimization often requires large data sets which are typically unavailable during the early research stage, particularly for emerging semiconductors such as 2D materials where pilot fabrication is costly. To address this, the paper proposes a yield diagnosis and tuning framework that combines ensemble learning and Bayesian optimization, enabling accurate yield prediction even with limited data. Using real fabrication data from 2D semiconductor devices, the framework achieves a mean absolute error below 8 and an experimented variance above 0.62, demonstrating strong predictive performance. Furthermore, implementing the model's tuning recommendations on a batch of devices led to a final score of 86, reflecting a 62% improvement in key performance metrics such as mobility and hysteresis. These results highlights the framework's effectiveness in facilitating rapid and efficient yield enhancement for novel semiconductor devices. Coming to the existing system states that in the current semiconductor device development workflow, yield improvement relies heavily on manual experimentation or expert intuition. Engineers typically optimize device performance by iteratively adjusting fabrication parameters such as temperature, deposition rates, and depoting levels, which can be slow and labor intensive. While traditional machine learning models have been applied to predict yields and optimize processes, these approaches usually require large data sets to achieve accurate prediction. For emerging semiconductors such as 2D materials, generating such data sets is expensive and time consuming, making convolutional ML methods impractical at the early research stage. As a result, the existing system faces multiple challenges. Experimental fabrication and testing consume sustainable time and resources. Data scarcity limits effective model training. Manual tuning is inefficient and inconsistent, and achieving optimal yield is often difficult. These limitations underscores the need for more efficient data conscience methods for yield prediction and process optimization in the development of novel semiconductor devices. Coming to the proposed system or base paper work. The proposed system introduced a data efficient framework for yield diagnosis and tuning in semiconductor device fabrication by combining ensemble learning with Bayesian optimization. Unlike traditional approaches that require large data sets, these methods can deliver accurate yield predictions and processes recommendations even with limited experimental data, making it particularly suitable for emerging and expensive semiconductors such as 2D materials. The system leverages real fabrication process data to train ensemble models capable of capturing complex relationships between process parameters and device performance. It then applies Bayesian optimization to identify optimal process setting that maximize yield while minimizing experimental cost. By following the model's tuning recommendations, engineers can efficiently enhance key device performance indicators, including mobility and hysteresis. Experimental validation showed sustainable improvements such as a 62% increase in yield, demonstrating the method's effectiveness, practicality, and potential for acceleration semiconductor device development. Coming to the dataset information, the dataset for this research stage semiconductor project provides comprehensive information of wafers fabricated under various experimental conditions to optimize yield and device performance. Each wafer is uniquely identified by an IoT ID and wafer ID and is associated with the product type and technology node being developed. The dataset records process metadata, including the process data and the specific tools used, etch, lithography, deposition, and implant tools to track fabrication variations. Critical process parameters such as etch rate, deposition rate, pressure, temperature, exposure time, and FAC offset along with implant conditions like energy, dose, and tilt angle are captured to quantify process effects. Device characteristics including critical dimensions, oxide thickness, resistivity, threshold voltage, leakage current, and resistance are measured for each wafer, while defect count and defect density track fabrication imperfections. The yield of each wafer representing the proportion of functional devices provides an overall assessment of process success. Together, these features create a structured data set that supports statistical analysis, process optimization, and machine learning approaches, enabling research to diagnose yield limiting factors, tuning fabrication parameters, and accelerate the development of emerging semiconductor technologies. Coming to the novelty or extension or enhancement or improvement. As an extension to the proposed system, feature selection was implemented using select K-best to identify the most relevant process parameters for yield prediction. An ensemble model was then developed using a voting regressor that combines random forest, gradient boosting, and XZ-boost, achieving a highest explained variance of 71.7, indicating strong predictive performance. In addition, all existing and proposed models were built and evaluated, allowing a comprehensive comparison of their effectiveness. To enhance interpretability, explainable AI techniques such as line and shape were employed to highlight the contribution and importance of each feature in the model predictions. Furthermore, a user interface was developed using the Flask framework, enabling users to input process parameters and obtain yield predictions directly from the trained models, thereby facilitating practical applications and experimentations. Coming to the flow of the work, firstly, we need to import the packages. This module involves importing all necessary Python libraries and packages required for data handling, visualization, pre-processing, and machine learning. It steps up the environment for subsequent models. Next, exploring the data set. We have generated the synthetic data set. Synthetic data is created to supplement limited experimental data sets, helping models learn patterns in early research stages. And semiconductor yield forecasting dataset. The actual dataset is loaded and analyzed to understand the structure, feature types, and overall quality. Next, we have data pre-processing. In data pre-processing, we have remove the null values and remove the duplicates. Missing data is handled to prevent errors in model training. Duplicate entries are removed to maintain the dataset integrity and avoid bias in predictions. Data visualization. Distribution of classification outcome visualize help understand the balance of yield outcomes or classes. Correlation metrics. It shows the relationship between the features, helping to identify redundant or highest corrected variables or highly correlated variables. Next, splitting the data set. The clean data set is split into training and testing sets. This ensures models are trained on one set of data while being evaluated on unseen data for generalization performance. Next, normalize the data. Standard scalar is applied to scale feature values to zero mean and unit variance. This step is crucial for algorithm sensitivity to feature magnitude such as KNN, SVR or gradient-based models. Next, we have optimization. In optimization, we have used grid search CV and Bayesian optimization. Grid search CV extensively searches predefined hyperparameter grids to find optimal values. The Bayesian optimization effectively searches hyperparameter space using probabilistic modeling for faster and more efficient tuning. Feature selection. Techniques like select k-best are used to identify the most relevant features that contributes to yield prediction, improving model performance and reducing complexity. Next, build the classification models. A wide variety of models are trained for yield prediction such as single models, ensemble variants, grid search CV optimized models and the extinction models. Next, training the models. All selected models are trained using the processed data set. Training involves learning the relationship between process parameters and yield outcomes. Next, we have the model evaluation. Models are compared using metrics such as explainable variance, mean absolute error, root mean square error, and R square. Next, comparison graphs. These comparison graphs are generated to visualize the performance of each model. Then, save the best model. The model achieving the highest predictive performance is saved for deployment and future prediction. Next, explainable AI techniques. Lime and SHAP are used to explain the model's predictions, highlighting the contribution and importance of each feature to enhance interpretability. Coming to the front end was developed using the Flask framework with user registration and login functionalities, supported by an SQLite database for user management. Users can provide input values corresponding to process feature for yield prediction. The system pre-processes user input in the same way as trained data to ensure compatibility in the training model. The trained model is used to predict the yield based on the user providing input features. The final predicted yield and associated information are displayed on the front end, providing an intuitive interface for users to interact with the system. The algorithms used are XGBoost, Random Forest, Light GBM, SVR, KNN, Gaussian Process, Navy Bias, Light GBM plus RF, Light GBM plus GOSS, Light GBM plus DART, Rigid, Lasso, MLP, ElasticNet, XGBoost with Grid Search CV, RF with Grid Search CV, and as an extension we have applied voting regressor and stacking regressor. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML template. These are the model files, which contains algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project. Firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. By using the command cd followed by a space and then paste the copied path. Click on enter. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. The homepage of the project should now be displayed in the browser. This is a front end built using the Flask framework. In this page, we have Home button and Get Started button. Now click on Get Started button so that the logout HTML will be opened. Here, you need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a password. Now click on Create an account so that all the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and password. Then click on sign in so that the prediction page has been displayed. In this, we have prediction button, graphs button, notebook button, and logout button. Firstly, we need to click on prediction button so that the ML powered yield prediction form will be opened, where you need to enter the semiconductor process parameters to predict yield using our advanced machine learning models. Now, let us give the input values and then click on predict yield so that the given inputs are pre-processed and the final output will be displayed. Firstly, technology node is 10 nm, lithography tool is 1, implant tool is 1, thickness uniformity is 1.673487. The critical dimension is given as 21.30141. Oxide thickness is 55.60491. The defect count will be 664. The defect density is 0.946658. Threshold voltage will be 0.557038 and the resistance is 90.02249. And now click on predict yield. Whatever the inputs are given, it is pre-processed by the ML models and the output is predicted as predicted yield is 0.7073 and the quality assessment is given as process stability is moderate, defect risk is medium, and overall score is B+. And we also have key parameters like critical dimension, defect deficiency, threshold voltage, and resistance. We also have some recommendations like fine-tune process controls, monitor yield trends. And production feasibility is given as production ready is partial, cost efficiency is medium, recommended action is optimize. And we also have 3D yield surface visualization. The predicted yield surface is shown here. We can zoom in and zoom out. Here it is given as predicted yield, critical dimensions, and oxide thickness. And next we have new prediction and view graphs. So again we can give some other new inputs and predict a new yield. Like technology node is of 22 nm, lithography tool will be 4, implant tool will be 2, thickness will be 1.95508. Critical dimension will be 27.18385. Oxidized thickness will be 53.88 568. Oxidized thickness will be 53.88563. Defect count will be 766. Defect density will be 1.089026. Threshold voltage will be 98.05319, and the resistant will be 0.281081. And now click on predict the yield. The yield is predicted as 0.3523. And here we also have the quick assessment, that is process stability is low, defect risk is high, and the overall score is C. And we also have the key parameters like critical dimension, defect density, threshold voltage, and resistance. We also have some recommendations like optimize process parameters, reduce defect density, review critical dimensions. We have production feasibility like production ready is no, cost efficiency is low, recommended action is revise. And here we have 3D surface visualization, which can be a movable one. And we also have predicted yield, oxidized thickness, and the critical dimension. Now click on view graphs so that the yield analysis data visualization graphs will be displayed. Now let us know about the each graph. First we have distribution of yield graph. The graph shows a histogram illustrating the distribution of yield values. The x-axis represents the yield range roughly from 0.1 to 1.0, while the y-axis represents the frequency of observations within each yield interval. The bars shows that most yield values cluster between 0.25 and 0.50, where the tallest bars appears, indicating this is the most common range in the data set. A smooth density curve is overlaid on the histogram, highlighting the overall shape of the distribution. The curve suggests a right skew distribution with a long tail extended towards higher yield values. This implies that while lower and mid-range yields occur frequently, very high yields close to 1.0 are much less common. The graph is titled as Distribution of Yield and uses a teal color scheme with semi-transparent bars and grid lines, making the overall patterns of yield frequency easy to interrupt. Next, we have predicted yield surface. The graph shown is a three-dimensional surface plotted titled as predicted yield surface. It visualizes how the predicted yield values changes as a function of two process parameters, critical dimension on the x-axis and threshold voltage on y-axis. The z-axis represents the predicted yield, with the surface colored using a gradient color map to highlight variations in height. The plot shows a distinct transmission in yield behavior. When the critical dimension is in the lower range, around 15 to 22 nm, the predicted yield is considerably high, forming a raised pleat with values clustered around the top of the z-axis. As the critical dimension increases beyond roughly 22 to 24 nm, the surface drops sharply, indicating a significant decline in predicted yield. Similarly, as threshold increases along the y-axis, the yield gradually decreases, especially in the region where the critical dimension is already high. The surface has a stepped and slightly irregular texture, suggesting the underlying model produced discrete or non-linear shifts as the parameters change. Overall, the graph illustrates a strong sensitivity of yield to critical dimension with a pronounced performance cliff, while threshold introduced an additional gradient base decline across the entire parameter space. And next we have top 10 features by select K-best score. The horizontal bar graph represents the top 10 most influential features ranked by their select K-best scores, showing which input variables has the strongest statistical relationship with the target variable. The feature critical dimension stands out overwhelmingly with the highest F score, close to 950, indicating it is by far the most predictive factor. The next strongest contributes a threshold and oxidized thickness, which also shows sustainable importance but at significantly lower levels compared to critical dimension. The remaining features including resistance, technology node, litho tool, implant tool, defect count, thickness uniformity, and defect density have noticeably smaller scores, suggesting they offer comparatively weaker predictive power. Overall, the chart clearly highlights that a small subset of features dominate the prediction strength, with critical dimensions being the most crucial driver in the model. Next, we have correlation matrix. The correlation matrix heat map summarize the relationship between all pairs of features in the dataset using a color scale ranging from deep blue for strong negative correlation to a bright red for strong positive correlations. Each cell represents the correlation coefficient between two variables with the values displayed numerically inside the squares. Notably, defect count and defect density shows an extremely high positive correlations up to 0.96, indicating these two features move almost identically and moves be redundant. Critical dimensions also shows a stronger positive correlation with oxide thickness and with threshold, suggesting these processes parameters tends to vary together. Most other feature pairs exhibit weak or near zero correlations, shows by cooler colors, meaning they are largely independent. The heat map provides a quick way to identify strongly related variables, potential multicorrelationality, and key interactions in the semiconductors manufacturing data. And next we have R-square graph. The bar chart is titled as Model Comparison for R-square. Summarize the predictive performance of multiple machine learning models using the R-square metrics. Each bar represents a different regression model, allowing a direct visual comparison of how well they explain the variance in the target variable. Overall, the ensemble approaches, voting regressor and stacking regressor, shows the strongest performance with R-square score around 0.71, indicating superior predictivity accuracy. Traditional random forest models also perform well, achieving scores above 0.64. Other tree-based or boosting models like XGBoost and various light GBM configurations show moderate performance, while simpler or more constrained models such as Lasso, MLP, and Navy Bayes yield much lower R-square scores, reflecting limited ability to capture the complexity of the dataset. The chart clearly highlights the advantage of ensemble and optimized models in achieving higher predictive reliability. Next, we have RMSE graph. The bar chart compares the RMSE performance of various machine learning models, showing how accuracy each model predicts the target variable. Lower RMSE values indicates better performance, and from the graph, models like voting regressor, stacking regressor, and the tuned variations of random forest and XGBoost achieve the lowest errors, making them the most accurate. In contrast, models such as Gaussian process, Navy Bayes, and MLP have noticeably higher RMSE values, indicating poorer predictive performance. Overall, the chart highlights clear differences in model accuracy and helps identify the top performing algorithms for the task. Next, we have MAE graph. The bar chart presents a comparison of different machine learning models based on their MAE, mean absolute error, where lower values indicates better prediction accuracy. Models such as voting regressor, stacking regressor, and tuned variations of random forest and XGBoost achieve the lowest MAE, making them the most accurate and reliable in this evaluation. Meanwhile, models like Gaussian process, Navy Bayes, and MLP shows higher MAE scores, indicating weaker performance. Overall, the graph highlights which model produce the smallest average prediction errors and therefore perform best for the given regression task. Next, we have explained variance graph. The chart compares the explained variance scores of several regression models showing how well each model accounts for variability in the target data. Traditional models like random forest and light GBM variants perform strongly with explained variance around 0.58 to 0.65, while simpler models such as navy bias, rigid, and lasso perform poorly. Ensemble approaches, particularly voting regressor and stacking regressor, achieve the highest score around 0.71, indicating that combining multiple models yields the best overall predictive performance in this comparison. Next, we have the Sharp feature importance graph. The Sharp summary plot shows how each feature influences the XGBoost model inside the voting regressor. Features like critical dimension, threshold, and thickness uniformity have the strongest impact on predictions, with higher or lower features values pushing the model output in different directions. Points spread further from zero indicating greater influence, while the color gradient blue to pink reflects whether the feature values is low or high. Overall, the plot highlights which feature most strongly drive the model's decision and whether their effects are generally positive or negative. Next, we have Sharp mean value plot graph. The bar graph shows the mean absolute Sharp values for each feature, indicating their overall importance in the model prediction. Critical dimension is by far the most influential feature, contributing the largest average impact on the output, followed by threshold with a moderate effect. Features such as thickness uniformity, defect count, oxide thickness, and defect density have smaller but still meaningful influence, while variables like resistant technology node, impact tool, and lithography tool contributes only minimally. Overall, the graph highlights which inputs the model reflects on most to make predictions with critical dimension dominating. And then click on logout. So finally, the project successfully demonstrates that early stage field diagnosis and tuning methodologies can significantly accelerate the development of emerging semiconductor materials. By integrating advanced characterization techniques with interactive optimization, we achieved improved device performance, enhanced reliability insights, and a clearer understanding of material level limitations. These results validate the importance of early diagnostic frameworks in guiding semiconductor inventions and reduce downstream development challenges. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.